Hey, Einstein fans, you're about to watch a special edition Startalk just for you, all about Einstein. Now, this is Startalk. I'm your host, Neil deGrasse Tyson, your personal astrophysicist. I got Chuck Nice, co-host.
Sir.
I got Jan Levin, old-time friend, colleague, physicist, expert on the universe in all ways that matter, especially for this conversation because we're celebrating the life and times of Albert Einstein. So Albert Einstein was born in Germany on March 14th, 1879. And Chuck, you know what day that is?
1879, March 14th.
March 14th. In any year.
In any year.
Yeah, what day of the year is March 14th?
I believe it's the day that precedes the Ides of March. But what is March 14th? I really don't know.
Before the Ides of March, that's Pi Day.
Oh, my God.
Yes.
Okay. I didn't know it was actually March 14th, but of course that makes sense.
314.
314.
Yeah, right. You get Pi to March 14th. When written in sort of the American way where we put the month before the day of the month.
Right.
Yeah. I mean,
exactly.
So 3.14. That's Pi Day. Then you get really geeky. And then at 1:59, right, 3.1415, 1:59 and 26 seconds.
Right.
And you get a full up pi moment.
Can I just suggest that that's probably the access code to every physics department in the world?
It's pretty funny. That's the 1, 2, 3, 4 of physics departments.
If you walk up to a sealed theoretical physics department, try 3.1415.
And you'll get it. Yeah. Oh my God, it worked.
And tomorrow, the missiles got launched, all because of Jana.
I shouldn't reveal these things.
So let's talk about this. So, Jana, what is the annus mirabilis, and why do we even say that in Latin? Why couldn't we just say it in English? His miracle year.
I don't know, why do we say it in Latin? That's a different question. We'll just talk about the miracle year first.
It's America, Jack.
Because so 1905?
Yeah, 1905.
1905.
How old is he?
25.
Yeah, 20. Yeah.
So Einstein was a clerk in a patent office, and he couldn't get a job in a physics department. His father was desperately writing to famous theoretical physicists saying, my son's really committed. And
like any dad.
He couldn't get hired.
Yeah.
One of his professors called him a lazy dog. And here he is in this patent office in Bern, Switzerland, and he has a drawer at his desk that he calls the physics department. And in this drawer, he has these scientific papers he's working on in between finessing other people's patents to make them better.
Wow.
And in that year, he has this extraordinary year where he publishes a series of 3 papers that absolutely transform modern physics. One of them is on the special theory of relativity. One of them is on Brownian motion, which refers to the atomic aspect of air and molecules. Like if you see a little piece of lint, you notice that it takes a zigzaggy pattern, and that's because it's all these little atoms
hanging on it.
And the photoelectric effect, which is staggering because it probes the wave-particle duality of light, that sometimes light acts like a wave and sometimes it acts like a particle.
Did this by the time he was 26.
Yeah.
Chuck, how old are you?
And unemployed.
Verify.
I'm 22.
Okay. There's still time.
I got time.
Okay, you got time. Thank you for verifying that. So they call it an annus mirabilis.
Why do we say it in Latin? Because it was all in German?
Did that get him a job?
Oh, yeah. Well, he did become, to the credit of the scientific community, even though this outsider was publishing these papers, it was very swiftly accepted, the significance of all of these papers, very swiftly. And that should also be a lesson to those many people who send me their theories, that when they're transparently correct, they are grabbed at with glee.
Right.
And,
all the most amazing, mind-blowing, earth-shaking scientific research was published in legitimate journals, accepted by peers.
Yes.
By peer-reviewed. So as they say, to be a genius is to be misunderstood.
Right.
But to be misunderstood is not to be a genius.
Oh, that's nice.
Yeah, that makes sense.
So you can't come to me and say, I have an idea, but the establishment is not, they're going to reject it.
Therefore, it's brilliant.
Therefore, right.
They don't get this, man. They just don't understand.
Right.
I'm starting a Facebook page for everyone to evaluate, so they don't have to come to us.
tell you right.
They just amongst themselves, talk amongst
Talk
yourselves.
amongst yourselves.
Yeah, well, now we have Twitter for that. You know what I mean? It's,
Now, he didn't call it special theory of relativity. So who called it special?
That's interesting. I actually don't know specifically the history. I mean,
Why do we have you on the show?
Because I could explain
Someone
relativity.
out there know why?
I mean, the general theory obviously came later when he included the curvature of space-time, but I don't know who actually coined it special. It was just the theory of relativity at the time.
Because the paper was on the electrodynamics of moving bodies. That's the name of that paper.
Yeah.
Of the special relativity paper.
Grabbing title. But the
Page
amazing
turner.
thing,
So that was 1905.
Yeah.
And then a general theory comes out when?
1915.
So that's 10 years.
Yeah.
And he basically pulled that out of
I mean, it's
the ether.
It's probably published in 1916, but it's like it's 10 or 11 years of struggling with the mathematics to elevate what we now call the special theory to the general theory.
Working alone.
Yeah, I mean, he was being influenced by people like Grossman, who was a mathematician. Hilbert was very influential. So Einstein wrote down several wrong theories along the way. And there's actually a kind of adorable story when he was thinking about something like gravitational waves, where he kept changing his mind in print. He would write papers, say they're
Adorable
real.
for a physics story.
yeah, well,
Was it?
The record.
adorable for a physics story.
Let the record catch that. Pause for a moment.
Right.
Yeah.
And right after this, believe me, we're going to get to some very darling theories.
So
Cheeks you just want to pinch. Yeah. All right, go
he
on.
writes a paper saying gravitational waves are not real. Then he writes a paper saying they are. Then he writes another paper several years later saying that they're not. And between acceptance of this paper and publication, he sneaks in a draft of a manuscript that says that they are. And one of his colleagues says, Einstein, you have to be really careful. Your famous name is going to be on these papers. And he just laughs. He says, my name is on plenty of wrong papers. You do not need to worry about that. So it takes him a long time. I mean, there's decades of him figuring out gravitational waves. And the general theory was 11 years, and he needed help from other people. He wrote down several
idiot.
wrong theories.
No.
What a deadbeat.
Einstein, you dumbass.
10 years.
Is that actually is that actually something that is? Did that do anything
In
to?
retrospect, that is short order.
Right.
Look at string theory. We're decades deep.
They're still in it for decades
Yeah,
after
it might
decades
be
after
it might be hundreds of years. I mean, there's no
And that's
human scale
dozens of leaders in the field.
really brilliant people.
And we have one guy, Einstein,
By himself.
basically. Yeah. No, I mean, I didn't mean to take away Jana's point that there are others trying to push things
Right,
along.
they're nudging him along.
Yeah.
Right.
They're nudging him along because he's actually putting something out there to be nudged.
Yeah.
Right? Yeah.
I mean, it was
good point,
really
good
interesting. It was really interesting that it was really him on the. I mean, largely there were other physicists, but him largely on the physics side and the mathematicians pulling him up because he was not actually the most sophisticated mathematical thinker. Another one of my Einstein quotes is, he says, you think you have a lot of difficulty with mathematics? You should see my difficulties with mathematics. So he was a very intuitive thinker. And he really originally rejected the idea that you had to do all of this differential calculus and this really elaborate mathematics. He thought that's ridiculous. It's totally overkill.
Pure thought
You could
should
just
be able to
think it through and it'll be like algebra. And he did that with the special theory. It was stunning, but he could not do that with the general theory. Wow. He had to step it up to be differential calculus on curved manifolds. No mean feat.
Wow.
Yeah, but it's pretty.
Yes.
Look, how did you do in
It's not
differential
only
was about to
adorable,
say,
it's pretty.
What grade did you get in that
Yeah,
class?
I was going to
John?
say that what I kind of go with is that you don't need that.
I know. You say, I will never
I
need
will
that
never
in my
need
life.
that in my life. Like I actually use that.
So, all right. So he does this. And then in 1921, he wins the Nobel Prize. So, but he did so many things. What did he win it for?
Well, he didn't win it for relativity,
That ain't right.
which
Wow.
is really interesting.
It's pretty crazy.
Yeah, was it the photoelectric effect? I think technically it was the photoelectric effect, or contributions to quantum. I don't remember the phrasing. Do you have the
okay.
phrasing?
No.
It was something
I
like
might do my notes
contributions
here.
to quantum. Like often they're phrased in a way that
They give you
removes it from a
latitude.
specific, right.
Yeah.
But it was not for relativity. And that is clearly his greatest accomplishment.
Wow. So it's kind of like if when an actor never wins an Oscar and then they're just like, all right, so we're just going to give you a lifetime achievement.
Well, he won it in 21, which is quite early in a way.
Yeah.
I mean, it was pretty soon after he proposed. It's not staggeringly late after he proposed this sort of revolution of quantum thinking. Yeah. And the interesting thing is that he never really accepted quantum mechanics, right? So he initiates this revolution.
What is up with Einstein?
Keep insulting Einstein.
But wait a minute. Is that his brilliance? The fact that he was so self-contradicting? Like he just, no, I can't. It couldn't be.
I think his brilliance is, I think there's something to that, which is his refusal to accept something he didn't actually understand.
That's a good point.
Okay.
Plus, there was it was hard to, you got to remember the era he came from the 19th century into the 20th century. This was the towering achievement of classical physics, where the universe was deterministic. If you tell me where to stand and I measure the motions and momentum, I will predict all future of this universe. That was a certain posture that the community of physicists has. Up comes quantum physics, where is it a wave? Is it a particle? Is that some percent of the time? And that, and who? And what was his famous quote? He was trying to tell God what to do. What was it?
God doesn't play dice. Was that the
Oh,
one?
yeah, God doesn't play dice. I'm telling God not to throw dice.
Right.
Oh, he tells God not to throw dice?
I think so. He said, no, God doesn't. I think as quoted by Niels Bohr or somebody,
right.
God doesn't play dice with the universe.
No, he plays roulette instead.
Roulette? He plays craps.
Plays craps, you know.
Well, then what does Stephen Hawking say later? God not only plays dice, but he sometimes throws the die where you can't see them.
Yeah, there you go. There you go. So
sounds to me like God's a grifter.
and then Einstein said something else at another point about God, and then Niels Bohr, I think it was Niels Bohr, said, Einstein, stop telling God what to do. He just got pissed off. So let me tell you if you agree with this, Jana. Okay. So this is my measure of why I think general relativity is a crowning achievement of the human mind, greater than almost anything else. Special relativity from 1905. I think there were enough people on the trail of that, that if Einstein were not around, special relativity would have been figured out within a few years of that date, maybe by 1910. Whereas general relativity is so different from how anybody was thinking, it might have gone another 50 years. And so this, for me, makes general relativity a greater singular achievement than special.
Wow.
I do think that you're right. It would have been many decades before it was discovered, if it had not been discovered by Einstein, general relativity. And that is intriguing.
Among your colleagues.
I also think it would have looked totally different. So Einstein gave us all of this. The general theory of relativity is a theory of curved space-time, and we follow the natural curves in space, and all of this elegance of geometry. Yeah. But none of it is necessary. There's a whole bunch of extra degrees of freedom in thinking about geometry that are not at all required. And I think what would have happened is that somebody like Richard Feynman, who was a particle physicist who was thinking about interactions of particles, would have discovered general relativity, but would never have hung all of this space-time language on it.
Right.
It would have just been masses,
would have had a different
gravitons.
A facade.
Yeah, it would have looked totally different.
And a completely different frame of reference.
Machinery,
right.
yeah.
Everything would have been, wow, that's incredible.
Yeah, I really think it would have been like, particles exchange light, and that's electromagnetism. This would have been particles exchange gravitons, and that's the theory of gravity.
Gotcha. Yeah. So was Einstein more of a poetic thinker when it came to these things? I mean, where do you get this kind of expanse and elegance that you can attach to what you're talking about?
I mean, I don't want to presume to know, but you do have a sense that here is a very visual thinker and very intuitive. And so all the space-time machinery, there might be excesses to it that are not formally required, but create such powerful imagery and tools that in that particular example, which is often rare, it's kind of the contrary of Occam's razor, where the extra machinery actually leads to better, clearer intuition than the total leanest abstraction of just particles exchanging gravitons.
That's beautiful, right there.
You should write a book or something.
Yeah. Book in there somewhere, isn't there?
Somewhere, man.
So, Jana, your book, The Black Hole Blues, it explored LIGO, just the quest, not so much LIGO, but the quest to measure gravity waves.
Yeah.
And what effort that would take. So how could you describe to me what's going on when two black holes collide and how they're going to give us a gravity wave? Why aren't they giving us gravity waves all the time?
Yeah. So in principle, they do give us gravity waves.
Are we giving off gravity waves now?
Yeah, right now, Chuck and I.
Okay, right. You
It's just pretty modest.
Right.
So if you think about how weak gravity is, like the entire Earth is pulling on me, and with my little arms, I can resist.
You can lift stuff away
Yeah.
from
Whereas
the Earth.
if it was charged, if there was that much charge pulling on me, I'd be liquefied. So gravity is incredibly weak. It takes an entire planet to even make it hard for me to walk.
That's a good thing then.
There's another quick calculation you can do. Back when we had a space shuttle that would launch people into space, if you took all the electrons out of 1 cubic centimeter of the nose cone, just remove the electrons and put them at the base of the launch pad,
That would be
the shuttle wouldn't be able to launch.
Wait a minute.
Because the electrons would
Just
be
the electrons.
in 1 cubic centimeter.
1 cubic
At the base of the launch pad.
Right.
They would be pulling on the leftover extra protons that are at the top. They would be attracting one another.
Right.
You would not be able to launch this.
Right, you could. Oh, wow.
So the
1 cubic
difference-
centimeter.
1 cubic centimeter.
Right.
So the difference between the gravitational attraction between like an electron and a positron and their electromagnetic attraction is something like a trillions. So it's that much stronger, the electrical attraction, than the gravitational
gravity.
attraction.
It's the gravitational pull.
It's weak.
It's like
So gravitational waves are incredibly weak, but so what you need in order to have any aspiration, even Einstein didn't think this would be possible because he didn't think anything in the universe could possibly bring space-time
pre-black
out
hole.
enough. It's pre-black hole. So you need something like the tremendous radical concentration of mass and energy in a black hole. You need them not only that, but you need them to be in the final throes of their orbits together. So it's like mallets on a drum. When they get closer and closer, they're getting louder and louder. And it's like this crescendo. So when LIGO made its first detection, it was the last 1/5 of a second of the orbits of two black holes, each one about 30 times the mass of the sun, a couple hundred kilometers across. They're going very nearly the speed of light, and they're executing, a few orbits in the final 1/5 of a second, and then boom, it's finally loud enough that even though it's traveling for 1.3 billion years across the cosmos, by the time it hits the Earth, if you think about the time it left, that just multi-celled organisms were differentiating on the Earth.
Yes, they were.
And there's this race, they're building LIGO, in the final 100 years, and then boom, when it hits, it's just barely loud
all
enough.
the while that wave is heading towards Earth.
That's right. But it could have been for the previous several billion years it's been ringing the Earth, but there was nothing there capable of detecting it.
Yeah. Now, is there any way that we could have missed it?
Yeah, many ways. So that actual night that the first detection was made was supposed to be the first science run of the advanced instruments. It was in September 2015. And they decided they weren't ready yet. So they canceled the science run. Wow. And instead they were there. It's like Sunday night, Monday morning, in the middle of the night, hammering on the instrument, trying to mess with it just as tests. They're literally driving trucks along the access road, slamming on the brakes to see if it screws with the instrument. And then in the middle of the night, they get exhausted. They put their tools down, they go home. The same thing happens in Washington State. This is in Louisiana. And within the span of an hour, this thing that's been traveling 1.3 billion years smacks the instrument.
Doesn't that tell you that this is happening more frequently than we think?
Way more frequently, because everyone told me, with the exception of Kip Thorne, that black holes would be years on, that we would detect all kinds of things first that we predict existed, but black holes were far off in our future, and they were not only the first things we detected, and it was beautiful black hole signature, but it was the first 4 things we detected were all black hole collisions.
Look at that.
Black holes all the time.
All black holes all the time.
Exactly.
So what's the future of this?
Well, a wonderful thing happened not too long ago. They made an announcement that they detected the first neutron stars colliding. So neutron stars are dead stars that aren't quite big enough to become black holes. They're under 2 times the mass of the sun, and they're dense dead stars. They're often highly magnetized. But the interesting thing, black holes are empty. They're just darkness, empty space. There's nothing there. So when they collide, it's in darkness. The black hole
Just
collision.
to be clear, when we say that a black hole has a certain size,
Yes.
that's not a physically
Right.
occupied volume.
Exactly.
Describe the size of a black hole.
The size of a black hole is really just the extent of the shadow that it casts on the sky.
By convention. That's
Yes,
what we,
by convention. It's the region beyond which light cannot escape. And so it is literally just the shadow cast on the sky. If you were to
three-dimensional shadow.
Yeah, if you were
cool?
to, yeah, it's really cool.
Okay, yeah.
Did you know you can have a three-dimensional shadow?
Yeah, it's like you should call it black ball, not black hole.
What could go wrong? The French already objected to black hole.
Did they?
Yeah. Trou noir. It's offensive in French, apparently.
Oh,
What do they call it?
A black hole. They gave in,
They gave in, yeah.
Couldn't resist forever.
Yeah. So that's the fascinating thing about a hole. When we think of a hole, we think of a circle in a horizontal surface that you go through in a plane.
Right.
Whereas this is a hole in three-dimensional space.
Right.
You can fall into
shadow.
from any direction.
Yeah.
Yep.
whoa!
And walking into the shadow should be as harmless as walking into the shadow of a tree. Nothing's there. You wouldn't notice anything. You'd cross right over. There's no dense material there. There's just nothing there. So when black holes collide, it's truly a dark event, which even though the first collision was the most powerful event ever detected since the Big Bang,
Okay.
none of it came out as light. None of it.
So can I ask you this?
If it did, it would be the brightest thing in the night and daytime
It would have
sky.
outshone all the stars in the observable universe combined.
So, okay, what if we don't see what's colliding? Okay, what is colliding?
Space-time itself.
Oh.
So the black holes blob together, and the shadow
Hold on for a second.
distorts.
Wait, just hold on. My head.
A bout of existential
Oh, God.
angst.
Space-time itself.
Colliding. Yes.
Then, like this blobby thing, it sheds off all its imperfections and it settles down to be one bigger black hole. So there's a black hole out there, as far as we know, about a little bigger than 60 times the mass of the sun, that's just wandering the cosmos aimlessly, completely dark and completely quiet. But the
I'm just a
fantastic
hole.
thing is they settle down.
Yes, I'm only a hole.
Don't get in my way.
So that's amazing.
Yeah, you see it you hear it in the recording that LIGO makes. You hear it ring down. You hear it settle down to a final black hole.
So tell me how 1.3 billion light years away, we can know it's two black holes, one 28 times the mass of the sun, one 36. What is getting modeled there?
Yeah.
Give us that confidence.
There's an old-fashioned mathematical problem, can you hear the shape of a drum? And it's very similar. If I bang a drum,
That's
I
beautiful.
think that'll be the title of my memoirs.
Can you hear the shape of
Nice.
the drum?
Can you hear the shape of the drum?
we all recognize sounds. Our phones go off and we're like, that's my ringtone. So it's kind of similar. We have a prediction for how the mallets, the black holes, bang on the drum of space-time, creating a sound. And it's a very specific prediction. It's not a whole range of possibilities. We can literally hear, if I played for you our predictions, the difference between black holes that were extremely disparate in size, it sounds different. If the black holes are on wildly eccentric orbits, it sounds different. So you can reconstruct the motion, size, behavior, spins, of the mallets, with some things less confidence than others. So like the spin of the black holes is hard to determine. They're both probably spinning. Some things with less confidence, but that there were two black holes with a pretty good degree of confidence. Yeah.
And with the masses that they were ascribed.
Right, with the masses they were ascribed. So you can tell how big they are too, because if you can hear the orbits, again, just like how you can hear mallets on a drum. And even
that's a weaker signal though.
Well, it is, but it's 0.7 times the speed of light, and you can tell when it's done one full orbit, and that tells you how big the system is.
Okay.
And that means you've got, these two black holes summing to a little more than 60 times the mass of the sun in a region only a couple hundred kilometers across.
All right.
So how are you going to do that?
Yeah, there's only one way.
Yeah.
Right.
So are there any black holes tiny enough that they spin and collide and create the sound of a triangle?
Well, it is fantastic that black holes that are just a few times to hundreds of times, 10 times the mass of the sun, something in that range, actually ring space-time in the human auditory range.
What?
Yeah, so the LIGO as an instrument
You told me
is
that once, and I said,
sensitive.
what are you talking about?
So LIGO as an
There's no
instrument
sound in space.
is sensitive to the range of the piano. So it's true, there's no sound in space because there's no air. And anyone who sees somebody screaming outside a spaceship is going to write complaints on Twitter that they don't know what they're talking about. But if you were near enough those two black holes, really near enough, you're ear could technically ring in response to the gravitational waves.
What you're saying is your eardrum that is normally set into vibration by vibrating air molecules, in this case would be set to vibrate by vibrating fabric of space-time.
Yeah, it would pluck it like a string.
Yeah, like a harp string.
Yeah.
Ooh.
Wow.
That's weird.
That is weird. That's
I
really
don't.
wild.
Yeah, I know.
like
You
it.
could if you heard that, get out. Move away. Imagine you would see nothing.
No, if you heard that,
You would see
it's
nothing.
too
but you
late.
It's right.
Right. Too bad it doesn't actually. Maybe that's what it says when you hear it. Instead of a
warning sign.
boom, it's just like a ha ha ha. You're cooked.
So what would hold my eardrums aside?
Mm-hmm.
What would my body feel if a wave went across my body?
So presumably right now there are black holes colliding all over the universe.
Right.
And we're being squeezed and stretched. But again, it's so weak that we don't even notice.
If it's strong, I say, ooh, I felt that. Or if it's reshaping the fabric of space and time and I occupy that coordinate,
yeah.
wouldn't I just shake with it and I wouldn't even know?
Yeah, probably most of these.
Get that, Chuck, what I was just saying?
Yeah.
If you're in,
You're-
if I draw a stick man on a rubber sheet and I bend the rubber sheet, the stick
Yeah.
man goes with
with it.
Yeah.
Yeah. So I think
Without
that's-
even knowing that he's being bent.
It's just, this is
Right.
how I'm doing it.
What the difference with the stick man is that we're bound together. So, for instance, your head is harder to squeeze and stretch than your eardrum.
Speak for yourself.
So, if you were there, your ear would start resonating more willingly than your head would. So, the fact that we're bound means we're resisting to some extent. So, the whole Earth, when the wave passes, doesn't really notice it. It's just so atomically bound to itself.
It would just be so funner
I think
if, in fact, we did.
Yeah, I think it's going to be more like for these long waves, it's going to be more like bobbing on an ocean, which is kind of what the mirrors in the LIGO instrument do. When the wave passes, they bob on the wave. It's not that the mirror itself is being squeezed and stretched. It's that it's starting to swing.
Okay.
And that's what you're looking for. You're looking for the motion of the mirror.
It's opened a whole new way of observing the universe. Is there any way to bring LIGO to bear on the Big Bang itself?
Definitely gravitational wave experiments, but probably not LIGO. So LIGO can put limits on the Big Bang. So the Big Bang might have actually made a bang. When the universe was created, gravitational waves probably really cacophonous. It probably sounded like noise. But it's outside of really the range LIGO's optimally designed to detect. It's much more likely that a space-based instrument like LISA, the Laser Interferometer Space Antenna, if it ever launches, that LISA would be able to detect the sound of the bang.
So it'd be a cacophony.
Yeah, noise. Just like... Right. Yeah. And so you ask me, how do you know it's black holes? Those two things sound really different.
Different.
Yeah. Wow. Black holes sound like... whoop. There's this...
That was good. Let me hear that again.
I don't know if I could do it again.
It's a black hole.
Called a chirp.
The black hole colliding.
That's a black hole colliding.
Those are two black holes colliding. Much less, macho than most people expect. It has this sort of sweet little chirp.
So has anyone thought about how you get a 30 solar mass black hole?
That's a really excellent question. So not only was the first...
I don't know how you make one of those.
Right. And not only did they detect the first gravitational waves, but they actually started probing new astronomy. We had no idea there were black holes that big. The projections were for much smaller ones. And now we know there's 160 solar masses. So maybe there are 100
Maybe there's
or 150.
some that are bigger than that.
Right. So did those already collide with other black holes to get that big? Or were they formed by direct collapse? Did they skip the Death Star state? Right. We don't really know. So that's already people are working on.
Yeah, because normally if you learn about black holes in your astrophysics class, what did you get in your
My astrophysics. I'm
taking it with me next.
much
semester.
Okay, excellent.
No, I got an incomplete. That was. I got an I. I got an I in astrophysics.
So we learned that one way to get a black hole is the end point of a high mass star.
Right.
Yeah.
But the high mass stars are 20, 30, 40, 50 solar mass, but they lose a lot of mass en route. So by the time it's done, you don't really have 30,
Much
40,
left.
50,
50,
60
60 solar mass.
No.
But now we know for a fact that we do have one because we
Right.
watched them collide.
LIGO picked them
There are
up.
some people that think they're pure dark matter, that they don't form from stellar collapse, that they're not the death state of a star, that they're an
And I'll tell you,
example of
I'll
dark
tell you
matter.
this, just as a vote for science here, anytime we have a new instrument that takes us into a parameter space where we had not previously looked, you discover stuff that nobody ordered.
Right.
Now you can
Yeah.
now a well-designed experiment is is thought up to test for something that you have an idea about, right? So we think we will detect colliding black holes. You do it, and oh my gosh, it's a kind of black hole we never even thought was there. Right. And so good science is that which shows that maybe you're on the right track to begin with, but then opens up whole new places that you never even knew. So now the next generation LIGO is going to know how to tune it, how to be better at what it is for the new stuff.
And they'll discover 60 solar mass black holes that will collide and say, damn, look out.
Look,
that.
No, it wouldn't be.
That's where you're going.
No, Chuck, it wouldn't be the 60s because the 60s would be more powerful than the 30s.
Oh, right.
So it would detect lower mass black holes or the 30 mass black holes farther away. Right?
Also, what about something we've never even thought of before? I mean, you think of the time Galileo first pointed the telescope at the sky, he's looking at Saturn, he's looking at the sun. He's not thinking quasars and black holes. Those things aren't even conceivable to him. And what we all really hope secretly is that we're going to discover stuff in gravitational waves that we couldn't possibly see in light. After all, 95% of the universe is completely dark. Right, exactly. So maybe there's something out there that we have not even thought of, and that is what everyone hopes for, to be honest.
Just think about that.
It's very cool, man.
Some crazy noise.
Yeah, because there's stuff we had no idea even existed until we opened up new windows of observation onto the universe. Right? Stuff that only talks to us in ultraviolet or in infrared. Until we had ultraviolet infrared telescope, it was not there. The birth call of the universe itself, the cosmic microwave background is microwaves.
Right.
Yeah.
That was a non-thing.
You got to see
we had microwave detectors.
Right.
Yeah.
Nobody even talking about
Yeah.
the early universe. So you could do that.
And now, thanks to them, we have Hot Pockets.
So can you give us just some final reflections on Einstein's life so that if we want to think, if we want to live, you know how a religious person would say, I want to live the way Jesus lived, right? So in the geek world, you say, I want to live the way Einstein lived.
Yeah.
Is there anything that you can tell us?
I really admired, above all else, Einstein's independence of mind and spirit. So when everyone else was saying, oh, there's something wrong with this supposition that speed of light is a constant, that just makes no sense whatsoever.
Right.
Einstein
Still doesn't really make sense.
It's really challenging. But Einstein accepts, and this is something that's often misunderstood in the idea of relativity, he accepts the rigidity of the constraint. That's what he does. And then around that constraint, he sees where he's free to move, and it's very limited. But from this tight constraint, he makes this, it's like squeezing a balloon in one direction and it blows out in the other direction. It leads to things that were so much more magnificent than just allowing the speed of light to not be constant.
You know what's interesting that you say that? I just thought of this now.
Yeah.
The worst thing you can tell an engineer is build this and there are no constraints and spend as much as you want.
Right.
It's like, oh my gosh, I don't know what to do.
Yeah.
But if you say it's got to be 30 kilos in weight, in mass, and it's got to use this much power, and it's got to fly in this way, and it's got to be made of these materials, go.
Right.
Then that's where the creativity.
Absolutely.
And so, for example, how do you get a telescope bigger than the width of your rocket into orbit? How do you do that? And people say, oh, okay. You tell the engineers.
Right.
They invent the telescope that
Unfurls.
Right. Who ordered that?
Think of that.
Who would have thought of that?
Necessity is the mother of invention.
Think of it because I didn't let you do something else.
Yeah. I think this
And
is
I
true
loved
art
your
too.
reference to Einstein in that context. It didn't constrain him, it liberated him.
That's
So
right.
I want to ask you
exactly.
something because you just sparked a question in me.
Make it quick, 'cause we're running out of time.
Out of time? Okay, so you said about Einstein and light being a constant. So when LIGO detected the pulsar, the
black
neutron
hole.
star.
Oh, the neutron stars,
the
yeah.
neutron star.
Yeah.
When they detected that,
Yeah.
did they make the detection and see the light at the same
Yes,
time
and this
since the
is-
light is a constant?
This is why everyone was incredibly excited. It might be, at the end of the day, the most highly studied astronomical event in history. Basically, some huge fraction of the entire international astronomical community turned telescopes, satellites, all kinds of instruments in the direction of the collision.
We do that.
It was a
We're
network.
good about that.
Astrophysicists.
we good that way.
No, I got your back.
We got your back. No, it's a very important thing.
amazing. It was
I'm in the middle of
thrilling.
my own research program,
Yeah.
and then in the old days, it would have been a telegram. Now it's oh my gosh, there's an event over here.
Gotta drop it.
And I have my detector, which is different from your detector, different sound. Now we have 9,200 different kinds of detectors getting different aspects at one event.
Yeah.
And you look at this part, and I look at that part, and I look at this wavelength, and you look at that wavelength, and you put that all together. You all eyes, all hands on deck.
Yeah.
All telescopes, check it out.
It was really remarkable. So LIGO caught about a minute in the recording, but all of these telescopes combined caught, a month. Wow. And it kept spiking in different wavelengths. It would go in the infrared, in the gamma ray, in the X-ray, and so all these different instruments had their time.
Wow.
Yeah, so that's how we roll.
Collaboration, international collaboration.
Got each other's back, guys. We gotta shut it down here. But Chuck, always nice to have you.
Always a pleasure.
And it's even more nice to have you. We'll find some excuses to talk about Einstein and the universe, just to get you back.
Love it.
All right, you've been watching and possibly only listening to Star Talk. I'm your host, Neil deGrasse Tyson, your personal astrophysicist, and as always, I bid you to keep looking up.